明治大学のルイス・ディアゴと申します。今回は 3D Printing with Kirigami Honeycombs っていうタイトルで英語で発表させていただきます。First, my talk will have a brief introduction about 3D printing and honeycomb technology, and then I will focus on how to use honeycomb technology to create a new type or a new way of 3D printing. So then to deal with this problem, we need to focus on how to reproduce complicated shapes. And for this complicated shape, we are just combining the origami simulator with a real XY folding machine we have been creating. And finally, I will show some simulation results and applications before concluding my talk. So first of all, in the morning, after I saw the presentation from Professor Narumi, I saw that maybe I don't need to talk too much about how to use 3D printing for origami, for creating origami. So I like it very much, the previous presentation. And in this presentation, it just gave us an idea on how we can use 3D printing for origami development. So, but focusing on this work and in our previous, my previous work, mainly 3D print, the relationship between 3D printing and origami folding robots. So we have been working on origami folding robots, but from the beginning, we saw that there are two groups or two types of folding robots. The one is what is called the self-assembling or self-folding robots, and the other one is that the robot which perform origami. So in the previous talk from previous professor talk, it's mainly focused on the self-assembling type of robot. So we have some stimulus and the pattern itself is a robot and it changed by itself based on this stimulus. In our case, we focus on the distress manipulation robots. So it means the right part where we try to make some machines to be able to fold the paper. So in that way, our previous work, so before entering in the honeycomb technology, I need to talk about the different type of pattern creating methodologies that also Professor Tashi talked in the morning about how to use Origamizer or Orirevo or Oripa. There are several programs to create origami pattern starting from 3D, but almost this pattern have been created to make by hand, or by self-folding robots. So in our case, based on how to create the machine to fold this paper, it's have been since a long time, since the work of Macon and Basin, they try to start making some machine to fold the paper, and just simple folding papers are very complicated sometimes to be realized. So in our case, we try to change, and instead of folding these complicated patterns, we try to focus on the great large scale production. I mean, try to create some 3D objects for mass production. So in that case, we need to simplify the pattern. So we need to work with simple patterns, and this pattern should be able to work on the production line. So for that case, we focus on the Kirigami. The honeycomb technologies. As you can see, it's a linear process where you can fold in line many parts. So, but the representation of this pattern is quite limited. So, the first work since 2006, Professor Saito and Nojima tried to represent not just plain pattern, but just some patterns with some curve. So they base their approach in using two curves, one in the top of the part, they call T, and one is the lower part of the panel. And in that way, they can represent more complicated shapes. As you can see, these two shapes, they can fold. They continues to be in only one line, but also including some cutting on the pattern. So, but also they know the limitation of these representations. I mean, they cannot represent any shape that like the shape we have today is in our 3D printer in STL format. So they try to extend the representation in order to deal with more complicated shapes. For example, Professor Said in 2016, they tried to extend use a polar coordinate in order to change the shapes in the depth, I don't know how to say, in the depth direction. So in the depth direction, they use polar coordinate, and they can scale the pattern in this direction. But in our case, also the MIT group, based on the Saito-san's approach, they use instead of using two curves, they use two surfaces. But the two surfaces limit the space, and from these two surfaces, they try to represent more complicated shapes, but almost all their examples are based on just two curves. So in our case, we try to represent any shape and also keep the pattern in the continuous manufacturing way, in order to be able to realize this pattern. So the main limitation is there are two limitations for their approach. One is the mapping approach. So when they have, for example, I represent that omega-1 and omega-2 are the two cross sections. So for example, if we have a T1 and U1 curves in the first cross section, and we want to map the first cross section to the T2 or U2 in the second cross section, we need to have two mappings, which are very difficult to constrain when we want to map from 3D to 2D. So this is the first problem they try to solve in the beginning using polar coordinates, but it's not enough when we have the shape of T1 and T2 are quite different shapes. So they have to use another type of function to be able to do this mapping. The other problem is that, as they describe in their paper, there are mainly four types of cells that when you use a honeycomb cell in the 3D, when you try to project this cell to the 2D, we have this type of four types of cells. One is the cutting is just a line, the cutting is just a curve, or you have a hole, like the third one. But the fourth case, they call this is a overlapping case, and it cannot, they say this case cannot be solved in the way they express by their equations. So in order to solve this problem, so we need to solve this problem to deal with more complicated shapes. So for that case, we use just 3 steps. The first one, instead of trying to describe the shape by two curves, one in the top, another one in the lower part, or two surfaces, we embed the honeycomb in the 3D. I mean, we have any shape, it's 3D shape in the middle, and we use the honeycomb, and using some Boolean operation, we can get all the position of the points in the 3D shapes. So with all this position of the points, as is shown in the right part, we have the description of the cells in the 3D space. So from in this case, we just represent one cell in the lower part with several faces, and the surface, the 3D shape, with the name, we name it S. So I'm using just the union of all these faces and the intersection with the shape, we can get all the 3 points in the surface as a result when we do the intersection between these faces and the 3D shape. So from these 3D points, once we have these 3D points, we need to solve the overlap problem, because the other cells, we can use the same equations developed by Professor Saito and Nojima, but the overlap part, we need to include some flaps in the pattern in order to avoid this overlapping problem. So this problem was also solved by the MIT group, and they did some kind of iterative approach in order to make this shift of the pattern while they are building the pattern from the 3D. In our case, you use a similar approach, but we try to speed up the processing time and just change the representation of the cells from using hexagonal coordinate system, and we just, instead of using this iterative approach, we developed some algorithm that we have to make two paths, and just to avoid this iterative approach and just receive almost the same result. So the main difference is in the definition of the cells and in the representation. In our case, we use constructed solid geometry to get the points, and the equations are just the same, but just using the two-step algorithm to avoid the overlapping problem. We also use some kind of optimization of the directions of the cells, but we are not. I will not talk about it in our today. So with this changing the direction, we can optimize the amount of materials in the pattern. So once we have the pattern, there are several machines, already existing machines, that can create this pattern. In the case of Professor Saito-san, also they have some pattern, and they developed some machine that they can construct these complicated shapes, but just as I said before, it's just the surface in the top and the surface in the lower part. The same for the MIT group, that they developed just some applications for the shoes, and they put in the shoes in the lower part the pattern, and they just also include some kind of absorption in the out of plane direction of the panel, using the Tashimura polyhedron to get absorption in the y direction. So in our case, what will be the difference? So the main difference is that the holes, we have the boundary is a complicated boundary, because it depends on the shape of the form. And also they have some holes inside the pattern, which are bigger than the holes in the previous approach, because in this case, we have included these flaps. So in our approach, we are testing this creation of the pattern. For example, in this case, it's a simple apple. And from the original apple in the left part with all the information, we just try to create it using the 3D printer. But when we have to create a 3D printer, we have the problem of thickness that was explained in the morning. And sometimes in this case, the pattern is not a manifold pattern. So we need to include the thickness, enough thickness to avoid the manifold, non-manifolds problem inside the pattern. So the middle part, in some cases when we have non-manifold phases, the automatically 3D printer program fills these cells in order to be able to print. In our case, after we now make some enough thickness, we can create the print in the 3D printer as usual. So in the same way, we try to use the machine to create the same the folding, or after folding this pattern in the top part, we can create some type or the same kind of shape in paper in the right part. So it is not so good. It is the current state of the machine. So in order to briefly describe what is the machine we have created, it's just instead of trying to do to simulate the hands movement of the person, based on our previous approach, we just created some machine which can create simple force in the up and down like an accordion force. But in this case, as we also need to make some holes, and we need to not only to make force in the direction of the movement of the paper, but also we need to move in the other direction. So we have two axes, X and Y, two movement for the movement of the machine. So this is quite a known problem for we have XY printers, XY machines that can be do the same thing. So in our case, we just modified our previous solution for one direction and include two directions. So in the Y direction, the paper, A3 paper is moving, and in the X direction, we have the end effector. And the end effector is the one which is able, it is in the red, we have a detail on the right part. We have from the upper part and also from the lower part. So in order to be able to fold in the up, down, up and down. And also in order to cut, we can change. We can see here, we have several tools. We can change the tools with these motors in order to be able to cut, to fold, and to glue at the same with the same end effector. So this is the key point of the machine. It is very simple, but the only thing we need to do is to change the tools when we need to change from the cutting to folding in any case. So I will just show some simulation results. Just for the simulation we are doing, we are using some databases. In this case, there is a database for 3D printer. There is a lot of 3D printing models that we can use to test our 3D printing algorithm. And also we work with the CAD models, but in this case, we are focusing in 3D printing modeling because we want to reproduce these 3D structures in STL format. So this is one approach we use. First, we use the simulator in order to validate that the mountain and folding lines are correct, and there is also not how to say, no crash in the pattern. The key point here is that the simulator, in order to define the path, in the morning there was a talk also yesterday, I don't remember, maybe yesterday, yes, it was a talk explaining that we need which path we should use in order to be able to create this 3D model. So in this case, the honeycomb model is quite simple. So we know in the sequential steps we need to do in order to be able to create this 3D model. So in the format, we have some they call opacity. So some parameters that we can modify this parameter in order to, if it is higher, the strength of the folding is stronger. So based on these parameters, we can fix or arrange which folding should be first, and to which step it should be stopped. So in that way, we can reproduce the 3D model from the simulator, and also we compare the result. In this case, it's a manual folding of the same paper, and looking the bunny for the different directions in order to visually evaluate the accuracy of the 3D model. So this is a pattern, and so the machine is just now we are in order we create a CAD model of the machine. We just made the CMSK multibody in order to simulate the machine, and because the speed of the machine is dealing very strongly with the speed of the paper, so we are just in the loop trying to modify which is the speed we need to use for the machine in order to create correctly the model of the paper. So this is some applications we are thinking about how we can use the 3D printer. I mean, this Kirigami Honeycomb for 3D printer. So for example, in this case, this is one application in soft robotics. We have a 3D, but we are thinking about if we can create, we have some advantage by changing the actuator by some Kirigami-based, honeycomb-based actuators. In this case, the lightness will be good because it will be light, but we need to test if it is strong enough to achieve this task in some actuators. So also we are trying to apply this for the medical to development of some medical devices. This is some scaffold, some bone that we want to reproduce using also the Kirigami, the honeycomb approach based on this pattern, and we are thinking how we can include this inside the bone and then develop, fold and unfold this pattern, very long pattern, but maybe we can include it inside the bond for their application. Also, another application is related with the architecture. So for the architecture case, there are some, in this case, we use some pavilion example, and we saw that if we create some pattern with only one piece of the pattern, we can fold it and unfold it on the plates in order to create some, in order to reduce the amount of manipulations of the plates and reduce the cost in the architecture construction. So we are not directly related with the architecture, but we think that this could be one application for the Kirigami base, honeycomb base on one continuous manufacturing process. So I don't know if I finished too fast. The main conclusion is that the Kirigami honeycombs have been created for complicated structures, and the new 3D printing technology could be introduced. This is just on the beginning, and compare with other traditional methods which use double cross-section. The proposed approach can use one sheet of material and be developed easily with the 2XY folding machine. So this is one example we show. As a future work, we would like to introduce also some absorption in the direction of the panel, the panel of the structure, in order to be applied to some jacket, for example, some shape-fitting structures. That's all. Thank you very much.